From here to the stars, I am your host, Stephen Euin Cobb. Our guest today is Dr. Pascal Lee. Dr. Lee is a planetary scientist interested in the history of water on Mars. Dr. Lee has led over 30 expeditions to the Arctic and Antarctic to study Mars by comparison with the Earth. He also studies asteroids and the two moons of Mars. His first book, Mission Mars, won the 2015 Prize for Excellence in Children's Science Books from the American Association for the Advancement of Science. Doctor, you are a planetary scientist at the SETI Institute. For those rare people who are unfamiliar with the SETI Institute, describe it and its goals, if you would.
SETI, well, first of all, hi, Steve.
Okay, thank you.
Good to be here. Thank you for having me. SETI, SETI stands for Search for Extraterrestrial Intelligence. But the SETI Institute actually does a lot more than that. While that was its sort of founding agenda, it quickly broadened its scope of research to the study of the origin, nature, potential diversity, prevalence, and advancement of life in the universe. And so by advancement of life, we actually mean things like spaceflight. Human spaceflight even is part of the scope of SETI, which is why I'm quite happy there, because I work mostly on human missions to the moon, Mars, and beyond, in addition to geology of planets. But the point is, it's no longer just the contact Jodie Foster scope of listening to possible advanced ET out there. It's definitely broadened to just understanding the potential diversity of life out there.
Okay, which is one of my questions. I'm guessing that you watched the 1997 movie Contact, which was based on the 1985 novel by the same name by Carl Sagan. In that movie, in your opinion, what did they get right and what did they get wrong?
I mean, it's a science fiction novel. I happen to have known Carl Sagan quite well. I was his last TA at Cornell in grad school, and he was a very rational, deliberate thinker. He, I think, allowed himself to write this novel because he was really intrigued by the possibility that there could be an advanced civilization out there waiting to be found. And he was also intrigued by, what would they want to share with us? And he came up with the idea that he thought was universal, that they would want to communicate somehow. And in fact, since statistically they would be, far more advanced than we are, they might actually provide us the means to go join them. So it's the notion of there being a galactic club of civilizations out there, and us being admitted as new members by allowing, a scientist, Jodie Foster, Eleanor Arroway was her name in the novel, by allowing Eleanor who incidentally was inspired by a true life character, Jill Tarter, who is actually one of the founding scientists at the SETI Institute. She's retired now, but she's still very active somehow. And Eleanor Arroway in Carl's book was based on Jill Tarter. And of course, Jodie Foster took on the act. But the point was, what did Carl get right and what did he get wrong? Well, it's hard to say, because it's a speculative novel. It involves, technologies that don't exist yet. It involves, I think, from the standpoint of human behavior and how, the Earth would actually respond to a signal that was actually intelligent. That was quite accurately portrayed, in my view. In other words, that's consistent with what I would feel would happen if we actually had evidence of an alien civilization out there. There would be a range of reactions. People who would want to hide, claiming to want to protect us. People who would want to sort of arm, claiming that we need to be protecting ourselves proactively. People who would want to communicate. who are just driven by curiosity and who and some trust in an advanced civilization for being smarter than just wanting to step on us. Anyway, I thought it was a beautiful novel. If it's reality, how close it is to reality or not, I think the future will tell. I personally think that we live in a galaxy where we might actually not be that many advanced civilizations. And in fact, I've been trying to make the case now for over a decade that if you sort of look pragmatically at the terms of the Drake equation, and the Drake equation, for those who are not familiar, gives you the number capital N of advanced civilizations in our galaxies. And by that we mean civilizations who are capable of interstellar communications. So by that definition, the Egyptians would not have been an advanced civilization. They would have been a civilization, but not an advanced civilization, because they were not capable of interstellar communication. And incidentally, this number capital N of civilizations that are capable of interstellar communication are just capable of it. It doesn't mean that they engage in it. That's very important, because some people argue, well, maybe they choose not to communicate, which is a possibility, but they could. All right. In any case, that number N is given by the multiplication of 7 terms. And if you knew each one of them, you would get the number N of advanced civilizations in our galaxy right now. And the terms are R sub-star, which is the rate of star formation in our galaxy, the average rate of star formation in our galaxy, times the fraction of stars that have planetary systems around them. So that's a percentage of those stars that exist, that form, that have planetary systems around them. So it's either 0 to 100%. We now know from exoplanet discoveries that many stars, if not most stars, have planetary systems around them. And by planetary system, we can mean anything from dwarf planets like Ceres or Pluto, or I hate that term, but what I mean is that they don't have to necessarily be substantial, large planets, all the way to big things, times the fraction of planetary systems, times the number of environments that are suitable for life in a planetary system. That's N sub E. So you have a set of planets. Not all of them would be conducive to life. Which ones are? And so the N sub E is the average number of planets or environments in a planetary system that are suitable for life. By that, we have to be a little bit geocentric. We have to look at what life on Earth really needs. And we define that an environment is suitable for life when there's liquid water available over long periods of time. I mean, liquid water is not life, but if you have a planet and liquid water persistent there for long periods of time, then presumably with the rest of the materials forming the planet, you have all the ingredients you need for life. So that's N sub E, times the fraction of those planets suitable for life where life actually appears, F sub L. That's also a percentage. It's not 100%, we don't think, but it's not 0% since we exist. So it's somewhere in there. Times the fraction of planets with life where life actually becomes intelligent. It's not an advanced civilization, it's just intelligent. Now there you can draw the line pretty much wherever you want, because not everybody will agree on how you define intelligence. I'm of the mindset, along with the SETI Institute, to define intelligence as humans appearing about 22 million years ago, when we started to be able to use technology purposefully to change our environment in our own favor, but in a way that actually can make improvement from one generation to the next. So, for example, the beaver uses technology, you could argue, to change its environment to its benefit, but the technique doesn't improve from one generation to the next. It's a instinctive behavior that is sort of improved incrementally through millennia of evolution. Okay, we're talking about father creates a tool and then son improves it, or daughter, and then daughter goes on to build the ark. Okay, so, or the bow and arrow. My point here is intelligence on Earth appeared only once, it seems, and it's a combination of just not only having the brains for it, because I mean, you can argue that dolphins and orcas are also very smart, octopi and orangutans, but they don't actually have the physiologic means, the hands, the access to the tools, access to a dry environment to really design, to really shape their environment to their advantage with technology. But that appeared 2 million years ago with Homo erectus, who for the first time was able to control fire, start fire as well, and also use stone tools for hunting. And then finally, the fractional planets where there is intelligence, where that intelligence becomes an advanced civilization. And so, again, that is somewhat arbitrary as to when do you consider a civilization that is becoming capable of interstellar communication. I put that in 1865 when James Clerk Maxwell, Irish physicist, came up with Maxwell's equations, 4 equations that are both somewhat complex but also beautiful, that explain how light and electromagnetic radiation in general, including radio waves, are essentially a combination of varying electric fields and magnetic fields. That's why it's called electromagnetic radiation. And so once you understand the physics behind radio waves or light waves, then you essentially have the ability to use them for communication, and that travels at the speed of light, which is interstellar class velocities.
Okay.
So then times the average longevity of a civilization. That's the last and 7th term. Now this is where there's a lot of arm waving. Some people will tell you that once you become intelligent, you can survive really for a long, long time, and why not 1 million years or even 1 billion? I was very pragmatic in my application of the Drake equation, and I didn't think that we could necessarily claim a lot more than 5,000 to 10,000 years, because that's what we have evidence for. No single localized civilization on Earth has lasted longer than that before it self-destroyed or got completely crushed by others. You could argue that we've been a single civilization since ancient Egypt 5,000 years ago, and even by that measure, we've only been an advanced civilization. Well, we've only been a civilization for 5,000 years, but still an advanced one since 1865. Mm-hmm. So we're very young as an advanced civilization. And, there's no telling how long we can last, because both the ability to have technology to modify environment can be an advantage, but I don't need to explain why it's also possibly the source of our impending doom, because we also create weaponry that's very effective at killing people, not to mention, biological weaponry that can get out of control. There are a number of ways we could be wiped out as an advanced civilization. So if you do the numbers pragmatically, taking the Earth as the sole example that you have, even if it somehow is not typical, but if you consider the Earth as being somehow representative, at least it's one data point that you have, you end up with, by my calculation, n approximately equal to 1. And so, it's not that we are here because of divine intervention. So you end up with n equals 1. Now, what that means is, first of all, each term of the Drake equation has huge error bars, some of them even by 3 orders of magnitude. The longevity of a civilization could be 10,000 on average, or 100,000, or even 1 million years. We don't know. So right there, that could change the numbers dramatically. But again, just using Earth numbers as your guide, when you don't have other data, you realize that n could be a small number. N equals 1. And if that's the case, we are it. We are it. And it wouldn't mean that we're somehow here by divine intervention or divine intent. It just means that in spite of how uh, prevalent life could be. So there would be many planets with life. There would be many planets with even potentially intelligent life. But planets with intelligent life and a civilization would, in the end, be relatively rare. And that's because, well, we get back to the because in 1 second, but that actually could have profound consequences, right? Because we could still be the product of a natural process of evolution of life, but yet a very rare outcome. And, that means that in spite of us being a natural product of evolution and biology, nobody out there really is about to come save us, visit us, teach us, send us instructions to build a spaceship. So in that sense, my guess is that Carl's novel was off because it's way too optimistic. But that's an opinion. That's not based on real fact. And if we're really alone, then it forces us to be really responsible. I mean, this one Earth that we have, we need to, of course, take care of it. But it's also the fact that we're going to be here for quite a while until we ourselves master interstellar travel, which I hope we can, and somehow, expand into the rest of the galaxy. So, most people will tell you that, oh, I'm sure there are advanced civilizations out there. They look at the night sky, and I think we want to, to consider ourselves open-minded in that way. We want to be open-minded, even in our culture. Star Trek and Star Wars, the premise is that the galaxy is teeming with advanced civilizations. I mean, there are bars out there where civilizations hang out, where some planets provide musicians. But I don't think we live in that kind of a galaxy. I think we live in a galaxy where we're just profoundly alone. And it forces both, us into a reality check, potentially, but also into a real profound sense of responsibility for our future and for what we mean. Now, even if there's only one advanced civilization per galaxy, there are many. There's about 100 billion, at least, galaxies like our own galaxy across the universe. So even at an average number of one civilization per galaxy, you're looking at, a universe that's teeming with advanced civilizations. But then the next one over is not, 10 or 100 or even 100,000 light years from us. Maybe it's more like, millions of light years. So there you have it. And the real reason at the root of this is that while life could be common, and I think life is probably common because it appeared very, very early on Earth. The oldest rocks that we have, which are rocks that were somehow laid down in a watery environment, a sedimentary environment. The oldest rocks that we have from Earth's early days that were laid down in a watery environment have signs of life in them, have biosignatures. So life appeared essentially almost immediately. As soon as Earth had ponding water, shortly after its formation, it was harboring life. And so that to me means that, the origin of life with enough water around and enough time will kick in very, very quickly.
Okay.
And therefore that could be common. But intelligent life on Earth, capable of creating tools to modify its environment from one generation to the next, that didn't show up until 2 million years ago, and through a series of happenstance events, at no point in nature did we ever come close to that. Dinosaurs had little arms and hands for hundreds of millions of years and never came up with the ability to really fabricate a tool to their strategic advantage. So that tells me that intelligent life is not a necessary outcome. It's just something that eventually showed up here, and that's why the math of the Drake equation tells you that in spite of how many planets there could be out there, even if there were 10 planets per star within our own galaxy, which has 100 billion stars, so you're giving planets to every star out there, 10 of them. The Drake equation gives you n equals 1. So, it's just because the slice of time that we have occupied as an intelligent life, 2 million years over 4.5 billion of history, is a very small fraction of time. And that basically points to the rarity of intelligence.
You are the director of the Haughton Mars Project at NASA Ames Research Center, and you established the Haughton Mars Project Research Station, which is relatively near the North Pole, at least if you look at it on a globe. That facility is now the largest privately operated polar research station in the world. What are the goals and activities of this project?
Well, thank you for asking. The Haughton Mars Project takes place. It's a summer field campaign mostly, although occasionally we go there in the winter. It's a summer field campaign that takes place on Devon Island in the high Arctic. Devon Island is the largest uninhabited island on Earth. It's about the size of West Virginia or Croatia, if that means anything to your listeners. I mean, it's even less populated than West Virginia. I say that as a joke.
Okay.
No offense intended.
Mm-hmm.
But it's the largest single expanse of rocky polar desert on Earth. Sometimes I'm asked, why don't you guys just go to stay in the U.S. and go to Alaska, or and that's because Alaska doesn't have polar desert. Alaska is cold but pretty wet. So is most of Siberia. So is most of the Western Arctic. Here we are in the Eastern Arctic, just along the west coast of Greenland. And it's one of the driest parts of the polar regions anywhere on Earth. And so Devon Island is polar desert. It's an environment that is cold and dry. I mean, it rains at most. Precipitation is about 13 millimeters of water per year, which is actually desert levels of precipitation. And on Devon Island, miracle, you have a large meteorite impact crater that's preserved. I mean, it's not a miracle precisely because it's so cold and dry, there's very little erosion going on, aside from glaciers. And so there's a beautiful large meteorite impact crater that's preserved. It's called Haughton Crater. It's 20 kilometers in diameter. Just to give you a sense, a meteor crater in Arizona is 1.2 kilometers in diameter. This thing is 20 kilometers in diameter. It's 23 million years old, so not that old. So now you have a place that is a rocky polar desert that's cratered with the ozone hole, and therefore high UV irradiation year round, well, except in the winter. You have the basic ingredients of a Mars analog. Okay, cold rocky desert with craters and high UV radiation. And on top of that, there's ice in the ground ice. There were ancient glaciers there. There's some even modern glaciers still present as well. It's basically Mars on Earth. And so I moved to California 25 years ago. I have yet to spend a summer in California. I mean, I did during the COVID years, but the rest of my life in the past quarter century, I've been to Devon Island every summer to explore that island, to understand why we see so many similarities with Mars. Is it a coincidence, or is it precisely because it's now the same type of climate regime as what we see on Mars? Cold, dry, water ice rich. And of course, it's not as extreme as Mars. It's still the Earth. There are many differences. Gravity is different, etc. But you take those differences into account, and you realize that what we have here is probably a mini Mars that can explain away a lot of the features that we see on Mars. Mm-hmm. So one of the big science conclusions that we've reached over the past 2 decades of working at this location pertaining to Mars is that we don't think that Mars was ever warm climatically and wet like most people assume. And this idea that Mars was basically cold and dry throughout its history, with still plenty of water at its surface, but the atmosphere, the climate was cold and dry is what we're talking about. The climate is something that we really proposed based on our field work at this location. And that's an idea that's slowly gaining acceptance. I mean, I sometimes say, I quote jokingly something that I got from Arthur C. Clarke. He used to say that, there are 4 stages to people's reaction to your innovative idea. Stage 1 is, oh, no, it's not possible. And even if it was, it wouldn't be a good idea. You give it some time, you keep working on it. Stage 2 becomes, oh, okay, it's possible, but it's still not a good idea. Okay. You keep working on it, you keep pushing the idea, you keep building your case. And then their reaction reaches stage 3, which is, okay, it's possible, it's a good idea, and I always knew it. And you keep working on it some more, and you get to stage 4 where, yeah, it's exactly what happened, and that was my idea.
Yeah, okay.
So that idea of Mars being cold climatically throughout its history and dry, with water and liquid water, of course, being present at the surface. But water and liquid water were present at the surface because the ground was warm. The ground on early Mars was warm. The planet was younger. It was volcanically more active. There was more heat coming out of the ground. Also, there were more frequent impacts. And so they, every time, would dump heat into the ground. Early Mars was warmer ground-wise than Mars today, but the climate was always frigid. That, I think, is the key thing to understand. And, like I said, the science community is slowly warming up to that idea, no pun intended.
Okay.
But it had a cold reception at first, like really cold. Okay. And again, I credit that to us doing our homework carefully on Devon Island over the years. Mm-hmm. Because what we essentially are able to explain is that a lot of these valley networks that we see on Mars that were attributed to water flowing at the surface of Mars were actually formed underneath ice covers. The atmosphere on Mars was never thick enough to allow water to flow at a trickle at its surface. And that's why climate scientists and geologists have been invoking a very thick Martian atmosphere to allow water to flow at a trickle on Mars early in its history. But you don't need that. You just need ice to cover the landscape, and then water. If the ground is warm underneath the ice, then water will flow at a trickle, sandwiched between the ice and the ground. Okay. So Mars essentially early Mars looked a lot more like Iceland today, at the boundary between ice and the warm volcanic ground. The atmosphere itself being, of course, on Earth, it's still pretty warm, but on Mars being really frigid. Okay, if you can imagine that.
Well, thank you, Doctor, for taking the time for the interview. It's great stuff.
Thank you, Steve.
That was Dr. Pascal Lee. This has been From Here to the Stars, a video series created by the Interstellar Research Group. The IRG is a non-profit organization dedicated to thoroughly exploring the science and engineering that can eventually open up the reality of interstellar travel. I have been your host, Stephen Euin Cobb. If you enjoyed this video, please hit the like button, and you can subscribe to our channel for other such videos. On behalf of all of us here at the Interstellar Research Group, I thank you.